We are rolling, so everybody, I will need your attention because the next speaker is an unusual one with a background in medical field, medically trained surgeon on the stage. Please welcome, round of applause, to Wassim Alhajomar, known as Wassimulator.
Hello. Hello and good evening. Am I on? Great. So welcome to Brecka. I'm extremely happy to be here. This is a breathtaking little town, and the company that I'm in right now in the last few days is even more breathtaking. I'm absolutely humbled to be in the company of so many intelligent people that I absolutely admire and have admired for many years. So today I'm excited to talk to you about a topic that I am very passionate about. But before I get into it, for those who don't know me, a little bit about myself. My name is Wassim Alhajomar. You may know me online through my handle Wassimulator on Discord and X and other places. I am a physician by trade, and I'm a practicing surgeon right now, located in Munich, Germany. In my free time, I tend to program. I've picked this up during med school. A friend of mine helped me get through it and introduced me to a very interesting course called Intro into C. That's how I got into the whole handmade hero story and how I got to know so many people over the years. Some of the stuff that I've made through my programming journey have been some of the stuff I finished making. Sorry, Eskil. Our AV Racer, which is a racing car game. I'll be talking about that a little bit in my talk today. Rebound Express, a little jam project, physical puzzler, and an open source project called Cactus Viewer, an image viewer, where I tried to solve the Windows Photos problem. So today we're going to talk about vehicles in games. Now, vehicles are something that you find as a staple of many games, of many genres, not even necessarily focused about vehicles. It's something that, it's almost something you expect whenever you have any kind of world that has travel in it, unless it's like a fantasy game. And there is a wide variety of different games. The experience is absolutely expansive. This is just a small collection of a few games that are out there over the years, and I've played a big chunk of those because ever since I was a kid, ever since I was yay big, I would try to pick up the next racing game as soon as it's available on the platform that I had. So the interesting thing about all this is that games create an experience. Racing games create an experience, and that experience is very variable. Interestingly, like it's not like when you're playing something that has physics in it, where you expect a certain behavior in physics, and it's either that or it's not very well implemented. When you have an experience of shooting games, when you have the weapons, you expect the weapons to behave in a certain way, and if they don't, then it feels weird. In cars, in vehicles, there's a variety of experience. Take this, for example. In this game, Mario Kart, it's the furthest thing from reality imaginable. You're sliding around, jumping in a car that is proportionately incorrect, and you're throwing things at your friends, but people love it. There's huge numbers of sales, and people enjoy this experience because it gives you an interesting experience. On the other end of the spectrum, you have something like this, racing simulators, where you'd have a guy who has a multiple $1,000s expensive racing rig and would be moving around and like honing their craft and practicing for many years in competitive online racing. And that is also an experience, and they're both vehicles, and the principles of how they were programmed in the engine are actually the same, the major principles. So programming cars in games and car physics in games is an art as much as a science, actually, and everybody does it differently. So why is that the case? Why does that happen? Because as I said, like when you have those physics-based games or RT or real-time strategy, or when you're moving a character, you expect a certain behavior. Why? Because we are intimate with that behavior from a first-person perspective. But when it comes to cars, the experience is not really necessarily first-hand. It's a second-hand experience that we map into real life, and a lot of it is coming from pop culture. We have this almost all of us have an understanding of what a racing car is supposed to feel like, even though very, very few have ever actually been in one, let alone driven it. So when we watch movies like this, we see the guy shift up 700 times in one race, and you're like, what kind of a great gearbox is that? Well, it doesn't matter, does it? Because in the end, what matters is the feeling that I am shifting up gear. So even a kid will know, I want a car that feels like I'm doing something when I'm shifting up gear. So the main question that you have to ask yourself if you want to implement a car in a game, and this is what the talk is aimed for people who are interested in doing that, is what experience do I want to convey? And the more important leading question is, how do I even implement that experience? So through my journey trying to figure this out, I realized that the problem is a little bit complex because of this variety of experience and the complexity of cars in general. You have to approach the problem from both sides. You have to understand the experience, and you have to understand the machine. And then somewhere in between those two, you'll find the solution perfect for your game design. So let me tell you a little bit about my first attempt. This is AV Racer, a very first draft. I had to pull up code from way long ago. You see here, I have a simple Newtonian model. It's a sprite looking top-down. I spent maybe way too much time on the art of this thing. But what's happening is that I'm controlling the position through acceleration and braking. I'm changing that multiplied by dt. The angle that the car is turning in is moving by an angular velocity that I actually smartly hook to the velocity so that it doesn't turn when it's standing still. And that's it. Now, this is as far as I could think of when I'm thinking about this. And I'm like, does this look like a car to you? It's not. This is, I don't know what this is. Something robotic moving on rails. So I went through a second iteration where I thought I would, where I thought I would make it a little bit more smooth. See, at that time, I didn't know how the physics worked that well. I thought, like, I understand the experience somehow. I've played a lot of racing games, so I need the car to slide a little bit when I turn, but the slide has to be smooth, so I started to implement smooth step functions and more of, like, non-linear analytical formulas that describe the movement of the car, and it looks better. I mean, like, it's sliding a little bit. It's drawing a trail behind it that's pushing the back wheels a bit. Now, when I did this, it was during the time where Casey was asking, like, does anybody have something to demonstrate? And I showed this to him. And he told me, doesn't this feel to you like the car is a little bit on ice? And I think I agree. The car looks like a floating spaceship moving around. It doesn't feel like the wheels are, like the tires are what's carrying the car around. It feels like it's all on a pivot, because it is, honestly. So I went to a third attempt because I was like dead set on faking this as best as possible. So I added even more magical numbers, and I did a parameter out of slidiness of the car so that it increases the slidiness the more the angle increases, and this changes other things through time. And I have no idea what's happening with the video, but you see the car now. This is actually something closer to the final version that I pushed for that game, and it really feels solid somehow. It feels fun to drive in the end. And this is what it looks like right now. Like you can find the detailed devlog on this game on my website, wassimulator.com, and this is actually also available on Steam. You can buy it now. It's not perfect. I was not happy with how hacky it was. There was a lot of fake variables. But in the end, the point I'm trying to make here is that if you try to focus on the experience, you can still get something interesting coming out, but you're always limited, because in the end, you'll find edge cases where this is not really behaving like the car you want to behave. But the important thing is you need to simulate the experience and not the machine. But also you need to understand the machine, because if you don't understand the machine, you're limited, and that's what connects both the two together. So after I did this, I thought, okay, my next project, I'm going to try to really do this correctly. And I looked online and started researching how do cars work. And I realized that I also need to understand the physics of how the racing driver experiences the car as well before I understood this. So doing that has brought me really much further than I ever got to with the previous car game. And I thought in this talk I would sum the things up that you should care about, the conceptual ideas, and how the general algorithm of how I implemented them and how I think like you could implement them, because I still haven't solved the problem. I'm still working on it, but this has brought me really far. So let's take stock of what we have to deal with. There are three main conceptual components when we're dealing with a car. The first one is the engine. Logically, that's the most important part for the car. Like, that's what you think about when you're thinking about the car. That's the thing that moves it. In this case, this includes the gearbox as well. In simple input-output terms, this is what takes the inputs of the player, which is the gas and the shifter, and outputs the speed to the wheel, and that synchronizes with the wheel because the engine is running at a certain speed that synchronizes with the wheel speed, and that's what's happening. It's multiplied by the gear ratio. The next aspect is basically the wheels and the tires. That one takes the input of the engine speed and torque from before the one before, and takes the input of the player, which is the brakes and the steering, and the weight load from the chassis above it, this simple thing that's sitting on top of it, and the friction with the road. And that's actually a very important aspect that we need to get into. What it outputs are the results of those friction forces that apply on the car, and also it outputs a speed that synchronizes with the engine. So there's this differential relationship that we have to also figure out, because the engine synchronizes the wheels, but the wheels also synchronize the engine. And the last aspect, and the simplest one, is the chassis. The chassis is a simple rigid body. This is the plug into the rest of your physics engine, because you hook everything to this part. It gets affected by aerodynamics, by drag, and by gravity. And wherever it moves the wheel. So that's its effect on the rest of the body. Okay, so how do games approach doing this? Because this is a lot of, it's way too high level. There's each one of those components is complex. Well, the reality of it, depending on the game, they cut corners. So the problem with that, the reason is you can't really simulate everything. I don't think anybody is really, except for maybe like the engineers in some basement at Porsche in Stuttgart, are really figuring out the fluid dynamics of the fuel moving through the pistons and shooting around. Nobody's doing that. In reality, in even the most complex racing simulators out there, at some low enough level, there's a black box, and that black box is just calculating something similar, something simple, and it's taking some input and churning out some output. While looking through this thing, okay, how do people then do it? Because it's starting to look like there's a million ways to do these things. Well, actually, there is a million ways to do these things. There's no definitive Bible out there when it comes to programming vehicles. Like, I can't point you to, okay, look at the implementation of that thing, and that thing is the solution. It's not that easy. And often, the really interesting parts and the crux of the matter is proprietary, because that's where there is a lot of competition of how to get this right. So in the end, you will have to choose the corners, like actively choose the corners you have to cut, you're going to cut. So you're not going to get that satisfying feeling like, I got the simulation right. I don't think you can, because you have to cut the corner at some point. So to put this all together in a visual form for visual learners, we have three components: the engine, tire and the wheel, and the chassis. There is a continuous differential equation on the horizontal axis. The engine is synchronizing its speed to the RPM speed to the wheels, and the wheels are synchronizing back to the engine. And the wheel itself is applying forces on the chassis. The chassis is moving the wheels, so there's this back and forth. The chassis hooks to the rest of your physics engine, and the meaty part of the tires of the simulation is actually the tire, because that's the thing that sticks to the ground, and that's the thing that generates the forces. All of the forces come from the tire. And that's the tire model, for those who know that term from racing simulation. So this is a general algorithm of how to do it in code, in pseudocode. Inside your physics step, you loop on each vehicle, you simulate its engine, and for each wheel, you have to do this on each wheel separately, which is what I did not do in AV-Racer. You update and simulate the tires, and in the end, you apply that to the chassis. And when you're done, you integrate, you do the collision, you resolve collision, the rest of the physics engine remains the same. So let's start with the first section, the first algorithm, the engine. Now, the engine is maybe conceptually the most complicated part of the car. It has the most moving parts. But in code, it's the simplest part of the code, because actually it's just a basic torque calculator. It cares about one value, and it updates just one value. So plotting some somewhat realistic data on how much power, torque, and rounds per minute Power is how much the power the engine generates. Let's assume it's always constant. In this case, it's 100 kilowatts. At a rotating speed of 5,000 RPM, it's generating 200 torque. Now that's way too fast for the wheels, especially if you want to start driving the car. So you have to scale that down. But by doing so, you increase the power. It's just a simple physics relationship. So the transmission scales it down to 1428. Differential scales it down 380. And in the end, you have, at the wheels, if you multiply it with the radius, you have a linear force of 9,500 newtons. It's a huge force that gets you a lot of turning for a smaller rate. Now, why am I telling you all this shit? Well, to understand that the power is also variable. Because for those who are intimate with cars and are fans of cars, you may recognize this shape of this graph. You have two curves, two hills near each other. One of them represents the torque, the other one represents the power. They're more or less conceptually the same thing. They're just, you multiply them through the drivetrain. If someone is interested with the formula, it's there. What you need to care about this is that if you want to make the car feel realistic, you will realize that depending on the RPM value of the engine, you get a different amount of power out of the wheels. So if you're driving around and you want to make the car feel real, you need to make it variable, even if it's not the exact same graph. You realize if you look up different engine graphs, that peak is sometimes lower, it's sometimes moving to the left, more to the right. Sometimes the slope is steeper, sometimes it's flatter. Each one describes a different engine. And that's the important point you need to take home out of this. So, okay, I understood that. How do I put this into code? Well, you fake it. I'm going to show you a little abomination that I did once. Whatever this is, I don't think you'll find this in any book because nobody does shit like this. This is just, I've been sitting around at Desmos for like an hour or two until I figured out something that looks like that curve with enough knobs that I can turn to play around with it. That's it. Because I wanted to have the ability to control the curve. Like, these are the things that you can do with it. The A value can adjust the curve baseline. The B adjusts its magnitude of the peak. C adjusts the end slope. D, the peak of the X position, blah, blah. This is where it looks like when you're playing around in Desmos. And you see, I have a lot of freedom working with it. And what I do with this is I just take that algorithm, implement it in code, and now I have a black box that can take an RPM variable and give me a power variable. And I can just put it in the engine code. Cool. So the next thing I mentioned is also that there's the differential, the gearbox. The gearbox is just a simple lookup table of ratios. That's it. Based on whatever gear you are, it multiplies the speed and reduces the torque. So these are graphs a car enthusiast might be familiar with. You have something like that gear ratio over there that plots the optimal gear. Like the first gear is the longest one. It goes up in RPM the more the speed increases, and then you switch to second gear, which then the speed drops of the RPM down to 5,000, and then third gear, fourth gear, and so on. And here we plot the power, the force that's been generated, and it's also like the strongest when it's the slowest speed, and then it drops down. Basic physics, but what you care about programmatically is just that lookup table, and you can tune these values, and you can make the car more aggressive in the acceleration, but less that strong in the top speed, and vice versa, and even more tweaks so that you can tune the car. Okay, that's another thing we care about. Well, let's put these together. How do I implement this? Well, these are the two differential equations that are the hardest to crack. I try to solve them this way. I mean, what the dr over dt is basically, I'm saying RPM plus equals this times dt. So I'm adjusting the RPM in one line, and I'm adjusting the wheel angular velocity on the other. This is something you have to solve in code. Well, let's look at the individual variables of how these work. So the RPM, the first component, you multiplied by the engine torque curve, that's K0, times the throttle input. So like you take how much percentage of throttle input is going, and then you look up the current RPM value, and you get a torque curve. That's how that torque value, you multiply that. Like you scale it somehow. You add to that. This is the solution I implemented for the differential equation. It's a spring. Basically, you take the expected value and the actual value of what the current RPM is supposed to be, the expected value based on the current wheel speed and the current value, and that scales it down so that the engine tries to synchronize with the wheel, and you multiply it by a certain scalar to make sure you get the right feel to it. The third one is just basic friction. The engine, when it's not hooked to anything, when you give it some gas and let it go, it slows down on its own because just friction power forces slows it down. So that's the general algorithm, 3 main components. You can add other ones depending on like little factors. Like in actual code, I also implement the minimum RPM and maximum RPM caps in this thing somehow like numerically. You can do some tweaks here and there. But that's the general way that got a good enough model working. On the other hand, the wheel's angular velocity does also something similar. There's the spring at the beginning. I'm taking the expected angular velocity based on the current RPM curve minus the current angular velocity. So like they're both trying to converge on the same point, and you multiply that also by the engine torque curve, minus the braking force based on the braking input of the player, minus just regular friction forces that caused any wheel to slow down based on loss of kinetic energy through friction. And those are the two relatively bigger beasts in the physics engine of the car. And in the end, and I need sound for this. Do we have sound? You have something that's like this. This is taken from my current physics engine of the car, like my current engine. I'm demonstrating the horsepower curve and the gear ratios, and I'm gonna let you hear the sound of the engine play. See, I changed some variables. And interesting here is that you're seeing some terms like bore, displacement, camshaft profile, turbo. Where does that go in all the stuff that I mentioned? This is all fake. This is all stuff that I am claiming have relate to it. I looked up what they actually do to the torque curve somewhere, and then I hooked them up to the magic variables in here, like the knobs, so that whenever I turn one of those, it affects those knobs. And in the end, you have something that feels like I'm tuning an actual engine where it's not. I'm not making a research simulation. I'm making something that makes you feel like you're playing around with an engine that somewhat correlates with reality. So that's the cool part about it. And here I can change the gear ratios, and I also hooked up all those variables to the sound generation. So now the sound generation also feels like, oh, whenever I change this aspect of the engine, the sound changes. Oh, so I did something when I bought that upgrade at the shop when I was playing the game. So for those who are interested, a little bonus of how I did that sound simulation for the engine. When I researched this, and I had to figure this out also for AV Racer, there are four major ways that people do this. The official way, that one that we have in AAA games, is sample-based. That's when you have a lot of money, and you take that money and you throw it at a studio that gives you microphones that you hook up to the vehicle in different position, and you record it at different times under different stress conditions. And you use all of those very expensive samples to come up with a smart algorithm that puts them all together, blends them, and you have something that feels and sounds really good. These are like games like Forza do stuff like that. Or you were penniless like I was, and I took one sample of like a rev and I just pitch shifted it. Sounded like absolute crap, and that's one of the main things that people say when they play that game, that the sound of the engine are not that good. But that's something you can do. What I currently do is audio synthesis. Like I synthesize the audio from sine waves and noise functions. That was really fun to work on. I'll talk about that in a second. Another one is model simulation, where you use samples of explosions, tiny explosions and tiny little samples that you play at a really concentrated frequencies, and you get an emergent sound out of that. And the batshit crazy version is the fluid simulation, and there's a guy you can look up on YouTube. I think some of you already know who I'm talking about. It's called Angi Yagi. He does a fluid simulation of what's happening at the engine, and through that has emergent sounds. Make sure you look that up on YouTube after this. So here's a general pseudocode of how I implemented it. I set a base frequency based on the current RPM, and then I calculate a few harmonics that relate to this frequency. Whatever harmonics, whatever base frequency, you just choose one. as long as the relationship is somewhat regular. And then I calculate how many frames I need to complete like 2 full cycles of that frequency. And because I have a custom engine, I have to send that sample continuously to the thread that runs the audio engine. For each frame, I generate bass noise. Make sure you generate bass noise because that contributes to like 50% of the feeling that the car feels real, and modulate that bass noise based on the RPM value. And then I calculate frame constant scalars that change the higher or lower the RPM is and the engine characteristics. And this is something I'm going to keep touching on. The more stuff change dynamically over time, the more realistic the thing will feel, regardless whatever thing you're making. The more knobs change in a regular fashion, but dynamically over time, the more it will feel real. And then I construct the sample through triangle sine wave, regular sine wave. I think there's also the saw sine wave and a noise modulated sine wave. And then it's like I add like a whistling sound for turbos and stuff like that. You can go nuts with this thing. And then you modulate the end sample based on the cylinder constants. And you mix all of those for a bunch of cylinders and you push it and you have that, what you just heard. Okay, so what I wanted to say is that you modulate things based on different characteristics and then you watch the magic happen. Okay, so that's that for the engine. Let's move to the second part. We were just having the potatoes, now we get to have the meat. The tire. The tire is the most important part of a racing game. If you get that right, you will have a car that feels right. If you get that wrong, it will feel wrong. Now the tire is it's a marvel of engineering. We've reinvented the wheel a few times, but actually we've improved the wheel a few times. And ever since we discovered that you can use vulcanization to make synthetic rubber, it has been a game changer because those things can move dynamically and blend, and they have a lot of potential elasticity in them. That actually that's the elasticity that moves, that generates the forces. It's when the wheel or the tire deforms and has that increasing elastic force is what makes the car move. So what happens at a smaller scale, to understand the physics, is you have a certain kind of gear, a rubber gearing. Like this is the tire that sits like right above the ground. The asphalt has ups and downs, hills and valleys, and the tire is hovering above it. When the tire sits down and has some normal pressure from above, the rubber starts to deform and it's no longer solid. But what it does, it starts to gear with the ground. What happens is that they're in middle positions where there's high pressure, there's some kind of elastic, the friction, the static friction is sitting on it. And those are the compression zones that you have as the wheel tries to turn. This also generates heat that changes the characteristics of the rubber itself. It improves the way it grips. All this is some physics. But the idea is that you understand there's some rubber gearing happening, and it's that what makes the thing. But the problem is that elasticity is not endless. Like it's not a fluid in the end. It's a solid. So it has a limit. And as long as you're within that limit, you can have a force and you can have control over the tire, because as soon as you leave that limit, the tire starts sliding. So now you're no longer controlling the tire's contact to the road. Now you can express those limits of elasticity in the force that the tire generates and plot that on a circle. And somehow, and you can break that component into longitudinal lateral components of what those forces are. This is how people studied this. So like, okay, a tire is driving around, turning left and right, and accelerating, decelerating, and we're getting measurements on how much force is happening. Let's plot that, calculate it, and okay, let's see what's happening on the longitudinal lateral components of it. And because we're realizing that you can more or less put a circle around the maximum force that the tire can generate. So let's take a look at those both components. The tire longitudinal components. In both of those topics, a very important distinction needs to be understood between what is static friction and dynamic friction is. I'm sure a lot of you already know this, but I will reiterate for those who don't. Static friction happens when, like, my laptop's sitting on the table. It's in friction. Like, even if I start to lean the table forward, it may stand still for a while. This is static friction. Like there's a friction between the thing and the table. There's actual kind of gearing happening at the micro level that's preventing it from moving down. And as soon as I move it, like I let it fall down entirely, it will start slipping. That's where you have dynamic friction. So understanding this concept of what static and what dynamic friction is really helpful to understand what I'm about to say in the next few slides. And you really need to understand those things. Like I'm not going on a big tangent with this, because if you understand this, it's really easy to implement afterwards. So static friction, let's imagine a tire that's sitting on the road with a normal force coming from above, and it's just rolling. It's rolling down the road. What the important variables we need to look at here is that what's the angular velocity of the wheel and what the angular velocity of the tire on the outside. It's equal. They're equal to each other. It's just rolling. It's the same angular velocity. There's rubber gearing happening and a static friction constantly happening on the ground. So that rolling tire, what happens if I hit the gas and I give it a little bit more gas? What happens? Well, what happens is that the inner wheel, that's the thing that drives the tire, spins at a slightly higher angular velocity than the outside tire. So it starts to deform, it starts to twist it. Now that discrepancy causes deformation of the entire tire. You have a compression zones in the forward position and decompression zones in the backward position, and this starts to stress the rubber. And this is what in the end generates the force. Now if I add too much power, this wheel starts to spin, start to have like, I can do donuts now. And at that point you might as well have like, they will end up having the more or less the same angular velocity, because now there's no twisting happening, it's just sliding on top of it. Now here's a nice video from Goodyear. I think some of you know this. You see how the tire deforms as the car starts to accelerate. And it twists like, okay, it's also getting static. It twists like mad. Now, no real tire twists this much. This is a drag racer. But the concept is the same. It's that twisting that's like the tire is resisting that twist, and resulting forward energy is pushing the axle of the wheel. So why am I telling you all this? Well, because the difference of the angular velocity is something we need to care about. And that thing is called the slip ratio. The slip ratio is a term I hate because I think it's a misnomer, but it's the official term that people use when it comes to these things. I don't think it describes really well what it is. I think it's just the difference between the driven wheel and the rolling wheel. That's the way it's defined by Society of Automotive Engineers as the formula above. You basically just need to care about the angular velocity of the wheel compared to the angular velocity of the tire. That's more or less what it is. Another way to express it is like this. That's by the Carlspan Tire Research Facility. Carlspan is currently actually working with BeamNG Drive in working on their tire models for that game. They get access to the nice toys. You as an indie developer don't. So, okay, that's the slip ratio. Why do I care? You care because of the next graph, and because you're here. The slip ratio, if you plot the slip ratio on the x-axis and on the y-axis you plot the normalized traction force that's generated, you realize there's a dynamic where the more increasing the difference of the angular velocity, the more it increases, the higher the generated traction force through those elastic forces are, until it reaches peak. And that's the point where the wheel no longer can grip with the ground anymore. It starts to slip. And so it starts to drop until you reach a point where it's just spinning. But even then, there is some traction force pushing forward. So like even the spinning wheel pushes the car forward a little bit. Or in the other case, if you're braking the wheel, you have the case where you lock the wheels, like when you see it in Formula 1 cars a lot, where they hit the brakes so hard that they lock the wheels and the wheel's just sliding forward, but it still slows the car down somewhat. So like there's always some generative force. But you can also see that the braking slip ratio, the curve is a little bit more gentle. It has something to do with where the compression is happening on the direction of the moving tire. You can look that up if you're interested, but it's not very important for this. The idea that you should care about is that there's a curve that looks like this that I need to somehow put into code. So to sum all this dry stuff up, the longitudinal forces are a function of the slip ratio, and a driven or braked wheel has a slip ratio that is not zero. A non-zero slip value does not mean that the wheel is locked or sliding, because the amount of slip ratio does not really correlate directly with whether the wheel right now is in a complete static or dynamic friction. It all depends on many factors. So like all of this is fluid it goes between static and dynamic friction. And perfect grip when you're driving around is when you are at a low enough but a non-zero slip ratio. This is for the longitudinal force. Okay, so how does this translate to code? Good question. You remember when I talked about the abomination that I showed you a while earlier? Somebody did a non-abomination, but it's the same idea, and it's an analytical function that describes those forces. That person is Hans P. Paseka, a Dutch-born tire scientist who spent the entirety of his life working on tires. And he came up with this beautiful formula up there with 3 knobs that you can work with. And those knobs adjust the magnitude, and they describe the way that curve moves around. And you can use something like this in code to come up with a number that you can help scale your forces by. So in the end, actual code looks like this. It's not that much. So I'm integrating the wheel angle. I'm calculating the contact velocity and the velocity of the rolling tire, and I am calculating a slip variable out of this. I'm plugging it through that, the Kalspan function I showed earlier, to calculate a slip ratio, and then I'm plugging it through the Paseka formula. And that thing gives me a good scalar that I can multiply my forces with. Here are a few examples. This is from my current project that I'm working on. In this case, you see that the back wheel is really spinning more than the front wheel is, and the back wheel is not really synchronized with the ground moving beneath it. This is because the back wheel has a very high slip ratio, you can see on this graph, and so the resulting force that's coming out of it is really low. On the other end of the spectrum, you have this case where while you're hitting the gas and taking your foot off the gas, you're slightly increasing the slip ratio, slightly not, and that's moving, it's generating a little bit of slip force that is pushing the car forwards, and the wheels are somewhat synchronized. So this is the behavior that the emergent behavior that you can get out of implementing this thing. Okay, so that's the longitudinal component. We can look at the lateral component now. That's the more interesting one. When we look at the wheel, now we were looking at it from this side, now we're turning it 90 degrees, we're looking at it from this side. When a wheel turns, it actually deforms around its contact patch with the ground. So like there's a lateral force that is deforming it somewhat like this. A demonstrative video, this is like a video of a rolling wheel on a treadmill where they're turning the wheel as it moves, and you can see the more the angle of the movement is, the more there's a large deformation happening at the wheel itself, at the tire itself at the bottom. Another example is also really cool. The higher the load you put on it, the more it deforms. Like here, it's trying left and right and then adding a little bit more pressure, and then trying left and right and then adding a little bit more pressure. And you can see like the deformation, like the patch is actually moving left and right now, increasingly. So what you need to care about when it comes to this thing are a few angles. In this case, we're looking at a tire top down, the front left tire of the car. The car is pointing upwards in this case. DC is the vector that's where the car is pointing. DW is the direction that the wheel is pointing. V, the blue vector, is the velocity vector of the wheel and the tire, of the wheel and the car. In this case, they're the same, but usually there's like some sort of angular momentum to the body of the car that changes the velocity of the wheel, but it's not important. The idea is that there's a general direction of the velocity of the wheel. And through all of those, you get 2 angles. You get an angle between the direction of the wheel and the direction of the car. That's like the steering angle. And a more interesting angle is between the direction of the wheel, and the velocity vector. And that angle is called the slip angle. We're like, wait a second, wasn't there a slip angle before? There was a slip ratio before. This is a slip angle. And this sheds more light why I hate those terms, because they're confusing. A slip angle has something to do with the lateral forces. The slip ratio has something to do with the longitudinal forces. Really easy to confuse. I would much prefer if they use like SL and no, SL and SL doesn't work either. So it has to be S longitudinal and S lateral. So what happens to the contact patch? That's what happened. What I wanted to demonstrate to you, like, so you can understand visually as well what's happening, because you don't really need to simulate this. This is what people at Tire Simulate, Tire Research Facility and Beam NG Drive do. So the contact patch deforms in the itself, like there's a position where it's in contact with the road where it's completely in static friction. That's where it's like immediately, like entirely pointing in the direction of the travel. And the rest is where it starts deforming. Now, tire engineers have seen that there's actually a very interesting distribution of forces that is not really constant all over. There's a whole thing we can simulate out of this. And this is what really advanced car simulators do. They add like testing points all over the contact patch so that they generate a different force based on different testing point. You don't really need to go this deep if you're doing just a regular car. But if you're interested in actual tire simulation and making a sim racer, this is how deep you need to go. But what you need to care about for this talk is that the central point is in static friction, the ends are in dynamic friction. That's more or less it. Here's a somewhat animated form, so you can see how the more the angle increases, how the thing deforms and starts to move. Also, the lateral forces push the thing a little bit to the right. You can see here it's demonstrated how the contact patch gets smaller, actually, the more angle you have, until you reach a point where you have a large enough angle that the contact patch is basically zero. That's where you have completely static friction. You're just slipping on the road. Now, where is this observed in real life? In the concept of understeer and oversteer. For those who, a lot of people who are interested in cars know this, but what this means for those who don't, understeer is when you want to turn at a certain radius and the car does not want to give you that smaller radius. So the car really doesn't respond that well. You have a larger arc. Oversteer is also the more scary one, the one where you lose control of the back wheels and the car starts to slip. On icy roads, for example, you have that, or when you're driving a rear drive car and you add a little bit more gas, so like the car starts to slip and you have that drift. This is what drifting is in the end. How that relates to the slip angles. When you're neutral steering, where you have full control of the car, the front slip angle of the front wheels and the slip angle of the front wheels and the slip angle of the back wheels are more or less the same. In understeer, the front wheels have a little bit larger slip angle than the back wheels, and oversteer, it's the other way around. Now, do I need to code this? Not really, because all of this is emergent. If you simulate the tire forces correctly, all of that stuff is actually emergent behavior. But if you don't do that, then you have to fake it, which is what I did for AV Racer. Show you a little bit more graphs. This is a general description of how the connection between the slip angle and the lateral force. You can also see it behaves the same way as the original graphs I showed you before for the longitudinal aspects. Increasing quickly, reach a peak, and then trail down. Another aspect we need to care about is that the force that's applied, the normal force on the wheel that's pressing it to the ground, also changes the behavior. So there's a lot of factors you care about this. The good thing is that all of this also can be simulated with the Paseka formula that I showed you before. So the Paseka magic formula can be plotted in. And the actual code for this is that it's just 4 lines of code. You calculate the angles that you care about. You plot it through the Paseka formula with certain knobs that you've twisted to fit a certain characteristic. And you have a lateral force. This is what it looks like. What's it playing? Wait a second. There you go. Now, in this case, you see here, as I'm driving around and turning, the position of the current generated slip force is changing. This is based on the front wheels. And I get that feeling that this is what causes the car then to move left and right. But the interesting part I want to show you in the next slide is what happens when I start to play with those knobs. Like I have here the front tires. I'm going to decrease the amount of generated slip force, and now I'm getting understeer. Now I'm turning the car left and right, and the car is not really responding to the direction I want to turn it. Now if I return it back, and then I go to the rear wheels, and I do the same, here I get oversteer. The car is starting to slide more. I'm getting a drifter all of a sudden. And all of this is just basically I'm chasing one floating point variable. That's it. That's the fun part about developing cars, is that once you get the building blocks right, you get a fantastic sandbox where you can test a lot of behaviors. And then you can, out of these changes, you can say, okay, what if I attach this to the weather so that maybe if it's wet, this variable goes down? What if I attach it to the how much wear there is on the tire and how much heat there is on the tire and so on? That gives me those results. So it's pretty fun. I recommend it. Key takes for the slip angle. The slip angle is the angle between where the wheel is pointing and where it's going. The lateral forces are a function of the slip angle. And the difference between the flip angles of the front and the back axle is what generates, what makes the experience of driving the car, of the stability of the car. Now, the larger the slip angle, the smaller the contact patch, the more you move into dynamic friction, the more you get into slide. And the vertical load also amplifies that. So the key take is that all of this is emergent, and the more parameterization you have in your code, the more it helps you in making it realistic. But it's not haphazard. If that parameterization is based on actual physical understanding of the models, it will help you a lot more. And this is what I touched at the beginning. The more things that are changing dynamically over time under different conditions, the more realistic it feels, because there really are very, very few real constants in physics. Now, the kicker in all of this is actually the most complicated part of this talk, and I don't expect everybody to understand. It certainly took me a hell of a lot of time to wrap my head about this, is the relationship between those two lateral and longitudinal forces and how they affect each other. Because I've showed you earlier, you can plot those in a circle, and this is actually one force that we're looking at. We're talking about one tire. We're not talking about two different things. So what happens is this, when we start to observe the curve of one while changing the variable of the other. Like if I'm looking at a curve that plots the slip ratio, like that's for the longitudinal force, and the braking and traction force that gets out of, this is basically the Pesega formula, by the way. And now what happens if I change the slip angle? You can see that as the slip angle above there increases, the more the curve deforms. So actually, depending on the slip angle, I have a different looking curve entirely. So like all of my variables that I was talking about earlier, the knobs, they need to turn themselves actually the more the angles are happening. Like this is also for the lateral force. The lateral force also changes depending on the slip angle. So all of this is also changing with time. So to sum it up, the longitudinal force is a function of a slip ratio. The lateral force is a function of the slip angle, and they both affect each other. Okay, this is where it gets complicated. So we talked about the friction circle before. I actually called it the range of elasticity before, but it's actually, people call it the friction circle in books. And this is where you try to conceptualize the maximum limit that you have of the combined force of the longitudinal and lateral aspect of the force by that quadratic formula, and how they affect each other. To visualize how they affect each other, what happens is when one increases, it squeezes the circle in a certain direction. Like in this case, there's a certain slip ratio that changes how much lateral force range you have. So like as the slip angle increases, it changes the limit of the longitudinal aspect, and as the slip ratio increases, it changes the limit of the lateral force. This is again why I hate the slip ratio and slip angle as terms. Like even without using them, it's hard to wrap your head about. Now you have something that's confusing you while you're doing that. Great. People have plotted that on combined graphs. So like here you have on one axis, you are actually showing the same graph as before, but they're both on one axis. So like this is how much lateral force is, like on the x-axis, you have how much lateral force on the top correlates with what slip angle. And on the vertical axis, on the y-axis, you have how much slip ratio connecting to how much traction force, and the combined force is then plotted, and you realize based on how much the other one or the other is, it changes. So you have this combined resultant force. This is, I know, this is you don't need to care about plotting this. What I want to offer you is that this is just a general understanding that this is these things are related and they affect each other. So you have resulting forces that you want to, like if you're at the limit, the resulting force is at the limit of that circle, that's how much force that you can generate. If you're within it, you are in a safe zone, so you can add more force generating to it. To make it a little bit more understandable in racing terms, there is this G traction circle, a GG traction circle. This is actually like you plot the G forces of a racing car while the driver drives it around, and you see the limits of that. So if we assume that there's a general limit, you can see like examples where you have, when you're fully under complete acceleration, that's where you're at the top. So when you're in complete acceleration, you don't have that much leeway in turning left and right, because if you're giving too much acceleration power and then you turn, you get outside of the circle and you start to skid. And if you're like turning at the maximum rate for the current speed you can't really add any acceleration or braking, otherwise the car slips. Like all of those, if some of you are interested in sim racing, you'll understand this, because this is what you start to learn, that you have a certain amount of grip available to you as a driver that you're trying to maintain within it. Okay, so people like plot those G-forces as the driver drives around the race. Like this is what it would look like of all the G-forces. Like the driver would turn left, right, accelerate, decelerate, and then you plot point. Like at some point he will go outside of the circle. That's where he loses control of the tire, and the race driver tries to maintain it, to maintain the limit. A more visual example is this one. This is what it looks like when a racing driver takes a corner. This is the circle down there, and we're color coding how the steps happen. First, you do maximum braking until you reach the beginning of the corner. So like we see here, you get maximum, you get increasing braking until you reach the maximum, and then you start turning. As you start turning, you're reducing the brakes because you don't have that much budget, so you have to reduce the brakes. And that's what they call trail braking. So as you increase your turning, you take your foot off the brakes until you reach a point your foot is no longer off on the brake at all. That's where you're maximum cornering. And then as you get out of the apex of the curve, you start to increasingly add more gas. That's where you get acceleration. That's where you're calling like unwinding steering. And then you have maximum acceleration when you're back on the straight line. This is what a racing driver feels like. And this is the stuff that you want to implement in your game if the person who's playing your game cares about somewhat realistic racing experience. So how do I implement this relationship? Unfortunately, this is the experimental part of every racing, every tire model. A lot of it is proprietary, like I said, and many people approach this differently. It's not that it's impossible, but a lot of it can be helped if you have an actual testing facility where you can test those things and you figure out through the graphs that you get out of it what kind of relationship, what kind of analytical relationship I can get out of it. There are certain models that are also available online, like the Paseka-Sharp model, the rated Filia and Dogoff. You can look that up if you're interested. Those can give you clues on how to implement this, but a bit beyond the scope of this. How I approach this, I do it twofold. After I calculate the individual longitudinal and lateral forces, I scale them down so that they would fit an imaginary normalized circle. I also change the knobs themselves, so that the constants of the Paseka formulas are also changing as the slip angle, slip ratio changes. So out of that, you get an interesting relationship that actually feels nice to drive. So to put it together, the tire's algorithm in code, in each simulation loop, you run the algorithm separately on each tire. And the result of that algorithm is two key changes. You adjust the angular velocity of the wheel. I showed this at the beginning through that differential equation. And you calculate the forces in the end that come out of three main points. The vertical force that is applied on the chassis, which is through the suspension, the traction and brake forces, the longitudinal aspect, and the lateral forces through steering and slip forces. Putting it together mathematically would look something like this. One thing I haven't addressed while talking about this is how do you do collision detection with the road for the tires? Now you can do it two ways. One way is through proper mesh collision. The tire mesh collided with the road, or you can do it as many car games actually do it, is through rake casting. So you cast a point from you pass a ray from the connection point of the tire down to the in the direction of the normal of the track, plus the suspension length, the current suspension length, which is just a spring, and then you get whether it's contact or non-contact. And that has borne fantastic results, actually. Doesn't need to be more complicated. And the last aspect of all of this is the chassis. This is not a huge section. It's actually just one slide. It's just your regular rigid body physics engine, because you're just simulating a box in the end that collides with the road. So that's the vehicle physics engine, in short. The three major steps, I put it also in somewhat kind of a graph that tries to visualize the direction of things. The one key thing to keep in mind is the blue line that runs horizontally. So you're taking the previous frames, because you're solving two differential equations at the same time. So you have to take the result of one of them in the resolution of the next for the next frame. So here in this case, I'm calculating the engine's RPM first, multiply by the gear ratio, and calculating the wheels angular velocity, and then I take the angular velocity for the next frame and so on. And I apply then the forces that I mentioned, the three main points, through 4 tires on 4 points on the engine. And you got something that looks like this. This is currently the current version of my engine. You can see on the right that even the curves are changing as the car moves around, because, well, let me go back and start it. You can see them as the car turns. The curves peaks are also moving. This is what's when I said that I was changing the curves as the angles are also changing. And the resulting experience actually feels somewhat like a car. It's not finished. I still have to tweak a lot of things. Actually, this whole talk has been one huge rubber ducking experience for me. I have many ideas of how to improve this through researching this, and I was stuck on this for months, actually. So I'm excited to get back to work on this. For any of you who's here in this venue, just let me know if you want to try it. I have it on my laptop currently. You can play around with it. And otherwise, you can follow me on Twitter, on X. I'll be having my my updates for my games there. And make sure you check out my AV Racer, at least on Steam. You'll be interested in trying that out. That's it. Thank you all for listening. Thank you. Thank you very much. And for the Q&A, I am absolutely thrilled and utterly honored that I'll be sitting on the same couch as Mr. Dennis Gustafsson, the architect and artist behind Teardown. So a round of applause for Dennis, please.
Thank you for the presentation, Wassim.
You're welcome. Thank you.
I am a little bit envious, I must say.
Really?
I remember developing the vehicle physics for Teardown was one of the most fun parts. You're in the middle of it,
yes.
And I can tell you, you're going really deep into it, and it just based on the look, on your energy, it seems like you're really enjoying it.
Yeah, I am.
Yeah. Really cool, by the way, you showed this video of the drag racing. I remember looking also at that. It's a really, really descriptive way of understanding how the wheels deform when you accelerate. And if I remember correctly, I'm not sure it's the same video or if it's a different one. You can see that when as the wheel of the dragster is spinning faster and faster, just by the weight of the rubber of the wheel and the increasing rotation, it actually expands.
It's true, yes.
Have you seen that one? It's really cool. And if I understand correctly, dragsters have only a fixed gear, and it's using this expansion of the rubber, so the wheel actually gets bigger as it goes faster and faster, as a way to have a bigger ratio, so to speak, between the engine and the road. I thought that was really cool. I just had to mention that.
I didn't know that myself. Yeah. Okay.
All right. So I have some questions.
Yes.
And the first one, I just looked at your screenshots. You have a lot of, and I also got the opportunity to try it out, so thank you for that. You have a lot of parameters.
Yeah.
Lots and lots of parameters. How do you manage all these parameters without going insane?
Well, I think it's it's important to categorize those parameters because some of them are related to actual things that are closer to the physics, like the Peseka formula or the formula of that abomination that I showed. These are like direct control parameters that I try to make them as little as possible. But then there's another layer of parameters that are actually just, they connect to those, that those deeper parameters affect those higher level of parameters. So like, as soon as I have this layering, the game is actually not that complicated because the higher level ones, I can just replace or change or adjust without really affecting the physics engine that much because the actual thing that's affecting the physics is simple in the end. At least I try to make it simple.
All right. Do you also have a way, if you are playing around, tweaking a bunch of parameters, like this setting was a bit better than the previous one, do you have a way to automatically apply those parameters back to the code, or are they saved in a file, or how do you?
I usually, whenever I have something like this, I have them periodically updated in a static file on Drive. So anything that I change gets automatically saved. And when I relaunch the game, so those things are live changed, as you can see in that thing. Like I change those things and they get read and loaded on the launch of the game, and they get stored during the game.
Cool, thank you. Also, I had a question about the update rate. I understand it correctly. You do the rigid body separate from the drivetrain and the tire model, and then you kind of feed them back and forth, the forces. Does that require you to have a higher update rate than you would normally have?
No, actually, I actually put them all in the same loop. Like they're all within the same loop. I'm looping over the vehicles in that time. So they're all running at the same rate. I haven't tried splitting the thing.
Yes, sorry, maybe I expressed it a little badly, but if you tick the game, say at 60 frames per second, do you have, is that whole tick, including both the tire, the engine, and the vehicle, is that more than 60 times?
That's more than 60, yes. I think I need to look that up, how many it was, but I think it's at least double, if not more than that. It's just many times more than that, and I split the physics step below that. Right. I'm not sure if I'm doing it correctly, but I've tried to separate the frame rate from the physics rate. So I keep calculating how much frame time is happening to fix the physics step. But it's currently not very performant. I haven't optimized any of that stuff. Yeah, right.
Yes. I also was wondering about the audio. It's pretty cool that you generate the audio procedure. I love that.
It's fun, yeah.
How close do you think you'll be able to get to, if you're aiming for realism, do you think, how much work would that be?
Exponentially increasing work, I think, because you can get something that sounds somewhat like it really easily, and every next iteration is going to get increasingly higher. I was actually interested in talking to Sander about his ideas of how to synthesize like certain sounds, because I don't know anything about audio synthesis, so all of this is just looking stuff up and trying shit. So I don't think I will get as close as reality, honestly. I think it's really difficult to get close to reality, but you can get something that's good enough. And that's, I think that depends on the goal of my game. I guess my game is not going to be a realistic simulator in the end. Maybe a simcade kind of thing.
Yeah. That was actually my next question. Whether you're aiming for total realism, or is this more on the like a fun experience?
I'd like to aim to as close to realistic as possible, as far as I can, because I think it gets to a point where also it's way too complicated for me without any external help. But I want to get this into, all of this is experimental. It's actually also my very first 3D project. So I'm learning about 3D rendering, about physics, about many things at the same time. So I want to get it into a position where I learn the technology, learn enough the technology so that in the next iteration I will decide, okay, this is the limitation I want to add for the game, or maybe make something fun out of this to as far as I could get it. Yeah.
Cool. Shall we maybe open up and see if someone from the audience has a question? One right here.
I wanted to ask a little bit about the RPM to power ratio for the engine simulation and some of the like transmission gear ratio kind of stuff.
Yes.
You mentioned at the beginning the like feeling from movies of like shifting up like 7 to 8 times, or there is actually a feeling I get when I try and do like a 0 to 60 test or whatever, right? Like where you're trying to get this certain spot where you're out of like power on one gear and you need to shift to the next.
Yeah.
Is there like something on those graphs of like this is the spot you're aiming for? Is there like some inflection point?
There is in the graphs. Wait, can I do? Am I allowed to do this? It was right before this part. Yes, you can see on the right graph that there's an area where there's a point where the first gear drops and hits the peak of the second gear. That's more or less where you would time your peak shift, because like there's a maximum amount of power for each one of them, and they start to overlap. And you can look up the torque curves of your engine, and you can visualize them as well. And then you can, I think there you might be able to come up with an analytical formula to calculate the recommended shift up and shift down. I think so, yeah.
Any other question?
This is a question for both of you, but how could... So I saw no mention of turbo lag, which in my opinion is the most...
Have you implemented turbo lag?
Well, it is in the audio file, but but no.
I think realistically you can do that, because you can add that to the part of the engine code where there is something that's like an increasing float that increases the more you're holding the gas until it spins to a high enough ratio, and then you add a number to the scalar.
Yet another like
Yet another one of those things in the differential equation, but it's basically just like one small variable that you count to. Yeah.
Masha?
I have a question related to chassis physics. That
Yes.
You said that simple rigid body box.
Yes.
So there are some racing games like going for really realistic approach, but they also have rough terrain. And when you jump from a cliff, sometimes they want you to land on your wheels always. But
Right.
without you losing the realistic feeling of that.
Right.
Like, and how would you approach that? Do you implement cut physics for the cars, or you?
I think probably you just do if no contact with the ground, then you need to take the wheel of the physics, and then you try to take control of the forces to steer it in a certain direction.
The tricky part is that it should still feel realistically, like
Right.
you want a car to do an arcade like flip back.
Right, that's true.
So maybe a cut physics to a car. I don't know. How would you approach that problem? How would you solve it?
Huh. Trying shit, I guess. I don't know. Yeah, you basically you cut physics. You at some point you just make an if condition if there is no contact the wheel in the ground, and then you calculate the trajectory.
I'm not saying cut like but a cat. Yeah, my pronunciation is really bad.
No,
Like
the
kitten.
animal.
Yeah, animal could like always arrives on his legs.
Yeah, basically, yeah. You as soon as you detect that you're off the road, you start to figure out in what direction you're going, whether you will be landing on your feet when you're getting there, and then add, I guess, increasing torque on the body of the car to fix that, maybe?
Yeah, it could probably be done in many ways. Teardown actually has a little bit of this.
Ooh.
And there is a parameter that you can tweak when you set up the vehicle, which artificially makes the distance between the wheels wider. Not visually, but you actually apply the forcer further out on the car, and that automatically stabilizes in all directions.
Interesting.
So that's a small trick.
That's the answer.
Yes.
Does the weight distribution of the car matter at all? Like the engine's in the front, and that's very heavy.
It does actually. Yes, it does. I don't do it correctly there. I have an inertia tensor on the geometry, calculated from the geometry of the car, but the car has like all wrong weight values. It matters a lot where the engine is, because that changes how much weight load is on the individual tires, and that affects the entire curves actually. This is where, yeah.
But it's like implicit in your curves that you use, or...
In the end, you multiply, after you do those curves, all of this is, the amplitude of that curve is multiplied like by the weight load, by some factor based on the current suspension load, like the vertical force. So like you calculate the vertical force, and then you multiply that by any resulting force you get in the end. So it scales it either up or down.
If you allow me, like, really quickly, so where do you find these curves, and like where do you find your research?
One book I recommend, it's called the Millikan. It's written by Millikan, Milliken. I think it was called Racing Car Dynamics. It's like an 800-page book. And the interesting, I did not read all of it, but the interesting part is also its references. So like he would also tell you like, this is my reference for this current chapter. And from those, there are also other interesting books you can find on this. And mostly there are books from the last century. Like the older you get, the more interesting it gets, because like there was ones that from the 60s, from like post-war tests on motorcycle tires and stuff like that. But the concepts are the same. But those books were really inspirational. They have a lot of diagrams and a lot of pictures that help.
You could like share it or something later.
I'll put it in the group. I'll put so.
So how many of these books did you read as part of the research?
I did not read complete books, but I think there are 2 large books that were my main references that I read a lot of chapters from. Like so the Millikan one and the one about the tire dynamics, I would have to look up to remember its name. Those are the main ones.
Did you have one here?
As someone who's never influenced the physics engine, to what extent is the order in which you're applying forces or possibly modulating different constants, to what extent is there a correct way of doing it, and to what extent is that an artistic choice?
Well, you need to integrate the last, like the way at least my engine works, and it's the first physics engine I read, so I don't know if it's good. I'm copying people's work mostly for this one. The general rigid body engine is that I integrate. I think I have it as the function. I think it's here, but it's not. Okay, so I calculate the forces of the engine first, which affects the wheels, which affect the chassis, and then I have like a collection of forces that apply on the chassis. What you want to do is you want to accumulate all the forces on the rigid body, and in the end you integrate those forces, so you change them. And the way I do it, which I'm pretty sure is not the perfect way, I think Dennis will correct me, you calculate the collisions then with other objects, and then I resolve those collisions. And that's like the general algorithm of how it works for each physics steps. But
you had the bidirectional forces between the engine and the wheel.
Yes, those happen. Okay, so I need to address that. So like, I start by the engine first. So I calculate the RPM value, which takes the angular velocity of the wheel from the previous frame. So like the current one that's available in memory actually. And I use that to calculate the RPM. And then downstream, as I get to the tire forces, I calculate the wheel's angular velocity from the current RPM that I just calculated. Does that help?
Is the choice to do it that way around, rather than wheels first and then engine, just like the engine is the...
I haven't really looked really deep into how much it affects each other, honestly. This is like the version that worked, honestly. But maybe Dennis has something.
I think you can normally see it if you see these like doing engine, wheels, and doing it. If you just line them up and not think so much about where the frame cut is, it's ends up being almost the same thing. So usually it doesn't matter so much. Yeah.
We don't have to bring this up necessarily, but I really like the slide you have about like the cornering like line.
Right. Yes.
I haven't seen the like friction circle before, and that visualization of like maximum braking to maximum steering to like whatever, right? That's something that like again you kind of get a feel for that as a human if you try and do like racing line like stuff. But one of the things I found interesting, the orange part, the like maximum cornering as you're like totally steering, no acceleration, no braking, looked like the most obtuse part. I guess like the least actual sharp angle. Is that just the way it was drawn?
Oh, I drew a racing line. I did not really engineer the perfect racing line out of it, but it's just basically to general idea. But yeah, that's actually a whole science of how racing drivers approach this, and it depends on how you set up the car and stuff like that.
So presumably that spot is actually like maximum like sideways.
That's you would imagine that's the place where you're getting the maximum sideways force while turning the car. Like.
Eskil?
The curve will also look different because your acceleration, your braking is not the same.
Right, yes.
So the maximum turning will not happen at the apex.
Right.
Unless your car has like exactly the same acceleration force as braking force. So therefore it looks it's different.
Thank you.
Thank you.
So have you thought about using more contact points per wheel to sort of approximate, a shape better?
I have, but I will do that as soon as I get this nailed down properly. Because like there's a lot of things I need to still fix in my code currently. Because this is the conclusion I got through while I was realizing where my mistakes are, and this is where. But all of this is like still work in progress. So as soon as I really nail down a model that is stable, that doesn't explode, that doesn't manage the edge cases properly, I would probably going to test how the tire deformation actually works. That would be very interesting.
All right. If we have no more,
Did you do any aerodynamics, like not real fluid dynamics, of course, but like
I just simulated aerodynamic drag, which is just a constant time, like it's a minus constant times the square of the length. That's it. It slows it down, but nothing more like the actual aerodynamic downforce. But I would like to do that actually.
I think we have one more, Raphael, right?
Yeah, it's just a comment on your talk. I've never seen these tire deformation videos ever before, and it made me feel some empathy for my tires. Like, unfortunately, I'm like, oh man, what am I doing to
my tires? Yeah.
It's another thing, you know.
Take care of your tires. Yeah.
Do I have one last question here?
Yes or no? It can just be yes or no. Are you gonna do anything with suspension, like when you accelerate or decelerate, like your car does, like something like this? Or?
It does that already. It's emergent. Like that's all you need to do is you need to apply the forces in the right position. It's already there. It already does that. If you look at the videos, it already does that. Yeah.
Yes.
Does your current system take into account the camber of the wheels?
Not currently, and that's a very good question because camber really affects this thing hugely. I didn't mention it at all because like it's another dimension of this thing, but it's in the end it's an angle of attack for those things, and it also has its own graphs.
So camber, I think if not everyone knows, is the what do you like a vertical angle?
Like if we're looking at the car from the front, it's whether the wheels are like this or like this. Right.
Toe in, toe out.
No, toe in, toe out is for when you're looking at it from the above and you do this.
There is this in as well.
Right. That's the Ackermann and anti-Ackermann angle and stuff like that. Yeah.
So anyone else? All right.
What should the slip ratio be called?
Actually, I like angle and ratio are good terms, but I prefer if they were called like longitudinal or lateral. Like if there was a word about longitudinal and lateral in it. Slong. Like longitudinal ratio and lateral angle or longitudinal coefficient, lateral coefficient, something like that. It would be much more descriptive in the name so you don't have tongue twisters. Yeah.
All right. I only have one final question before we cut, and that is, do you have one of those racing rigs at home?
I have whatever I could afford. Like I could afford a GeForce, I think it was 926 or something. And I have a VR and I got into iRacing and stuff like that. I do. Oh. I have them at home. Yeah.
Cool. All right. Round of applause.
Thank you. Thank you very much. I'm honored. Thank you.